you are doing through workflows is that you also like creating content specifically for
I don't comment section. I'm saying that you can.
we're able to do that.
I'm streaming.
I said, no,
I'm streaming.
so
Can you hear me?
working on, I think Thursdays and Saturdays, right? Yeah.
Are you live?
Thursdays and Saturdays. So normally you were supposed on Thursdays you have like I don't like the theme was kind of sorry, next thing is like so Tuesdays and Saturdays. So now on your Tuesdays you're also like supposed to be creating content specifically for traders in the community, right? Okay, you've done that. Okay, then that's fine. So what's going to happen is for the you need to like help Peter with this one just to get everything ready.
Hello. Hello guys, can you hear me?
I think that will be okay. Can I stay here?
Let me know.
Can I stay here?
I don't know. For the meantime.
Yes, I didn't know you were talking.
I'll be holding a class. I'll be having a class, huh? Okay, can you hear my audio? Can you hear what I'm saying? Is it her voice you're hearing? Hello guys, if you can hear me, please leave a comment on the... Okay. Hello guys, can you hear me? Okay, this is it's lagging. You can go with it. I think we're clear. This is it's lagging, but we're fine. Okay, can you hear my audio? Can you hear myself? Okay. We'll be starting the class at exactly 4 minutes past 11, or let's say 5 minutes past 11. Let's give the other people an extra 2 minutes to join the session. So we'll be going live exactly in the next 2 minutes time. All right. Okay, thank you. Give the other people an extra 2 minutes to join the session. So we're going live exactly in the next 2 minutes time. All right. Okay, thank you. Extra 2 minutes to join the session. So we're live exactly in the next 2 minutes time. All right. Look what I'm doing. You drop the link. Huh? No, I don't have to. You post it. Okay.
I'm going to use this so currently people will not be able to join the meeting because
let me see a recorded session. They can watch it later.
So message me earlier yesterday. Like currently we cannot access it because
No, cool.
you're also like reach out to me about that.
Let's start.
Okay guys, I'm hoping we don't have any issues with regards to technical technical issues. So hoping everything is set on here. So we'll just get started. So welcome everyone. My name is Amobi Njubisi, and this will be our first lesson in this series of the machine learning project we'll be building together. So we'll have over 10 different projects we'll be going through together, and this is just the first one in this series. So today we'll be looking at real estate modeling, how we could model real estate, use machine learning to build a model that can help us predict the price of a real estate property in California. We'll be using a well-known data set from scikit-learn, and we'll be going through this whole thing together. So again, welcome you all. Welcome, and once again, congratulations to our fresh graduates. So we have a whole journey to go through together. So from here onward, it's ideal for us to just build, get your hands dirty, find any data set you can lay your hands on and just build something. The more you do, the better you get at it. There is no way around it. So you just want to keep practicing your skills and all the things you've learned over the years, or over this whole month, this journey, and you'll get better in no time. So we'll walk through this process and then we'll see how this unfolds. So without further ado, I'll just get into it. So the way this is going to work is that this project is going to last for a week, right? So today we'll run through the model, and it's going to be an end-to-end sort of arrangement. So we'll run through the model for today. We'll see what the model looks like. It's not going to be a perfect model, so to say, because we haven't finished fine-tuning this model yet. But at least you will see just exactly what it takes to get started on the model, work it and rework it until you get it to the point where it starts to look reasonable. Okay, and then tomorrow someone is going to take you. So after the model is done, we're going to see a simple UI interface where you can display the model and see how it produces results, so that if you're going to present something to end users or stakeholders, they might want to see what you've done. So we're going to be looking at a simple interface where you can present your model having done them. And then thirdly, we'll also see how to deploy your model to the cloud. So essentially, this is a complete package, end to end. So you want to be a complete, a full stack data scientist, going through your process, your project, whatever project you're working on, going through it from the very start to the end. So that will give you a good, a generalized knowledge in what you are doing. All right, so having said that, I'll just dive right into it. So for start, we will be importing our regular libraries and packages. By now, you're nearly all familiar with all of these libraries. So we have our scikit-learn. So we have a scikit-learn library. We'll be importing the California data set. So here it says, let me expand my screen a bit so you can see what I'm doing here. So from scikit-learn, the data set will be importing the California housing. So it's just an inbuilt data set. So if you go to your scikit-learn data set, there are a lot of data sets you can work with on that library. Okay, so you want to maybe explore with that furthermore to see some of the data sets you can easily get from there and get your hands dirty. So, but for today, we'll be using the California housing dataset. And then we have our pandas, matplotlib for visualization. Then we have Seaborn for visualization as well. We have NumPy for numerical calculations. And then we'll be using scikit-learn for our train test splits. You're already familiar with this. Or standard scaler for scaling our algorithm, our data sets. And we have linear regressions, and then our error and accuracy measure calculations, and then all of these libraries that you're already familiar with. So we don't have to dwell on them. So you don't have to run this now, so we don't. I'd already run them before. Okay. So. Okay, regardless. So next, we load the data sets. Having imported libraries, the next cell here is to load the data sets. So this is how we load the data set. We just call the class. We'll call the fetch California housing class. When we imported it up, here, fetch California housing. So we call that class in our next line here. We instantiated it as California housing. So having instantiated that, the California housing right now is holding the X value, the X variables of your data sets, and then the Y variable. So all you want to do is you want to extract those. You want to extract those singly. So this is how we do that. So I'm going to say california.data. So california.data here contains all the X variables for this data set. And then I have the features name, right? So that's an extra, so that the columns will contain, I'm extracting the features name from california.housing as well. And then I'm passing that to the data frame, so that I can create a fresh data frame here. So, and then I'm doing the same thing, but for Y, since my Y is going to be the target variable, which is going to be a single column, so my Y is going to be a series. So I'm doing a california.target, and then the name of my data set here is medHouseVal. So I'm going to show this data set so that you see what it looks like, so that you can have a feel of what this data set looks like. Okay, so I extracted X. These are the predictor variables X. This is a response variable Y. So, but then I want everything in one data frame. I want everything in a single data frame. So what did I do? I had to use my x.iloc. Okay, x.iloc, created a data frame of it, and then created a new column with my Y value. So that's what happened here, because the X value here is not it's a data frame though, but then I want to create a fresh one because I already made it into a data frame. So I want to create a fresh one with my Y value. So that's why this. Okay, so then I have my data frame with my X and Y features. So that's what we have here. So I'll just walk you through this data set so that you can have a feel of it. So this data frame will try to predict the house value in California. So this is called median house value. That's what we'll be trying to predict using the various response features of median income. Median income. So the way it's clustered is every observation in this data set is in reference to a particular cluster in California. It's not based on a single house, but a particular cluster. So it's clustered into, let's say, maybe not region, but clusters of home, you know. So in this so every observation is representing a cluster. So for the first one, we have median income. Median income. So in a particular cluster, what is the average income that people within that cluster earns? And then we have house age. That's the median age for houses within that cluster. And then we have average room. Again, the average number of rooms in the houses within that cluster. The same with bedroom. Then population, the average population of the people, the population of the people within a particular cluster. And then we have average occupation. Okay. Sorry, average occupants. This is not occupation, but occupants. That's the number of people living within a house in that particular cluster. The average number of people living within a house in that particular cluster. Then we have our longitude and latitude to help us with location. And then the median housing value. That's the value of a house within a particular cluster. Okay, so that's what the data set. That's an overview of the data set. So going further, we try to do, so the way you work with a new data set, if you have your data set, you might want to do quick exploratory analysis. You want to have a feel of your data. You want to see what it looks like, what the distributions look like of the different features, and especially your target variable. You want to distribute it and see what it looks like, whether there are outliers, whether there are missing values. You just want to drill down to have a good feel of what the data set looks like. So we will not be doing all that detailed job, for the purpose of having this, not overextending this period. So, but for what it's worth, this is a .info outlook. So the .info is telling me that everything looks good with these data sets. In way of structure of the data sets, like I don't have any missing value, I don't have any null value, so everything looks good. And then it's all float 64 variables. So far everything looks good. All right, and then moving on, I want to do a quick distribution to give me a sense of what I'm dealing with, right? So this model will be using a regression. We'll be running a quick regression on this data set. So, but before I do a regression, I at least want to see my data set to know if it's linear. If your data set is not linear, then doing a regression might not be the perfect thing to do. So I want to do a quick regression on this model, a quick distribution of the model, draw a quick scatter plot, a quick histogram to see what the data looks like, whether a linear regression would be ideal for us. So, and then the way you go about this is, so I just did a quick one, which is pair plots. Pair plots would actually compare every feature with the other feature. So it's a plot that tries to, plot out all the features with themselves, with one another, just so you see whether there are linearity or whether there are multi-collinearity as well. So I'll be explaining all of these details as we move on. So a quick one again, just to help remind us of how you work with a data set if you want to do a model. So if you've done your exploratory analysis, you've looked at the data set. So before you decide on what model you want to do, if you're going to do a linear regression, the first thing you want to do is you want to see if the data set is linear. If it's linear with reference to the target variable, okay? If it's not linear, then it doesn't matter whatever work you may have done. It doesn't matter whatever you do. You're not going to get a good result because it's not linear. So you'll be shooting off regardless of how good your model is. You'll be shooting off because from the very premise of your model, you picked the wrong one. So that's why you want to do this. So looking at this, I'll just go down so we can make sense of this? So these are all my features, right? And then at the very tail of it, I have my medical housing value. Okay, so this is my median house value at the very end of it. So comparing my median house value with every of the other features to see what we have. The first plot here, or this last plot here, I hope you're seeing my cursor as it moves. So this plot here at the very tail end here, the median income versus median house value plot shows a bit of linearity, because we can see a bit of trend. It's not perfectly linear, but we can definitely see that there are some trend on here. We can see some linearity in this plot. And then if you look at the next one, which is the house age versus medical house value, this by no means, there is nothing linear about this plot. Okay, and then we have the average housing, and then the median house value. A little bit, but we really cannot call this. So this looks like so we have the majority of the values clustered around 0 to 50. So this is average room. Okay, so we have the majority of the values clustered in a very tight region. And although this would not do a good job because we haven't scaled these values yet. So essentially we're dealing with not very good distribution here. So I can understand why this might not exactly show us what we might want to see. So, but again, the linearity here is not very strong. And then for average bedroom, it's equally not very strong. So we have population versus house value. One would have thought that population should actually determine that the more population you have in an area, that the house values in that area is supposed to be representative, is supposed to be high with respect to population. But for some reason, that's not the case. That's not the case. And then, even though that's not, we can see the sense in that, because sometimes population does not actually tell exactly how valuable a property would be. Like if you move towards the slum, to the lower end of an urban city, you see that the population there would be high, and then the prices of homes might not be as high, right? And then if you go towards the higher end regions of an urban city, yes, the population might be less, and then the prices of houses would be high. So sometimes population might not give you the exact sense of, even though intrinsically house values are supposed to go up as population comes, but then if you drill it down, it might not exactly tell you the entire picture. So that's what we have here. That's why population here does not really is not entirely linear with house value. And then we have average house occupation, and then latitude and longitude is not very linear as well. So for the most part, our data set is not entirely linear with house value. It does not correlate entirely with house value. So, but we wouldn't leave it at that. Let's still drill down further to see what we have. So if you've done your scatter plots, and then you've seen what it looks like, the next good thing to do is to do a heat map. A heat map can help you see the numbers. So it's not enough to see the visuals like we've seen already, but you might want to see the numbers. Just what are the exact numbers of our linearity, of our correlation? So that's what we have in our next plots. Looking at this plot, this is our median house value again. And then we can see, so the red ones, So your correlation, your heat plots, correlation matrix heat plot goes from 0 to 1. So 1 means high correlation and 0 means no correlation. And sorry, it goes from minus 1 to 0, 0 to 1. Minus 1 means highly negative correlation, and then 1 means highly positive correlation, and then 0 means no correlation. So this is our 0 mark here, which is the light color here, but deep blue here is strong correlation, and deep red means strong positive correlation. So looking at it, on the diagonal, we have all 1. Yes, of course, we have all 1 because the features correlate. Means no correlation. So this is our 0 mark here. The features correlate with themselves, right? So median income correlates with median income, and housing age correlates with housing age. These are all 100% correlations. Okay, so let's look at some of the features that stands out. For the most highly correlating feature is our, okay, so we were basing this with our medical median house value. So for median house value, the most correlating feature is our median income, which is 0.69. So 0.69 is the most correlating feature with median house value. And so we also have 0.1, which is the age of the house. 0.15. We also have negative 0.14, which is the latitude. And then the rest of the features essentially are 0.0, which means correlation is very minimal. Okay? Correlation is very minimal. All right, so keep that in mind. And something else I'd like to point your attention to is these other red zones. Like we have 0.85 average bedroom versus average room. Okay, you see this high correlation between average bedroom and average room. So this is what we call, this is an indication of multicollinearity. Okay. Multicollinearity is something you want to be aware of. As you work with your data, you want to be aware of it. Because if you have observations that are multicollinear, they can impact the way that your model would come out. So we have average bedroom and average room strongly correlated. And then also we have latitude and longitude strongly negatively correlated, 0.9 to 0.91. Okay, and again we have, okay, that's the strongly multicollinear features we have here, which is, and this makes sense. And the reason this makes sense is, let's say for instance the average bedroom and average room. So the number of bedroom you have in a house would essentially correlate with the number of rooms you have in a house. You get, so if you have more rooms in a house, that's directly means you have more bedroom, indirectly. So as the number of rooms increases, the number of bedrooms are supposed to increase. So that's a direct correlation. So in regression models, you want to be aware of them so you can take care of them. Otherwise, they would affect the way your model would come out. And the same thing with longitude and latitude. So if you have a longitude in a particular area, you automatically have the latitude as well. So whatever the longitude of an area is would definitely determine what the latitude of that area would also be. So it means that one feature is telling us what the next feature should be. So that's a correlation. We don't want that. Okay. So there are a number of ways you deal with multicollinearity. And by the way, that's the next thing we check in our model. So we've checked for linearity. We can see that it's not very linear. All right. Next, we want to check for multicollinearity of the features. So if you find out that some of your features have multicollinearity, there are a number of ways you deal with them. You might want to do a log function of the features. That might take care of it, right? You might want to do a log function of the features, or you might want to pick a better model. There are certain models, instead of your simple linear regression, there are better models that takes care of multicollinearity. And then so we'll be looking at all of this as we move on, but just keep them in mind. All right. So just a quick one, just to remind you that you can ask questions as we progress. So if at any point you have any question, just drop them on the chat. Just leave them on the comment section. We will revert back to them when it's time to address some of these questions. If there's anything that it's not very clear to you, and then you want clarity with some concepts, please do not hesitate. Just drop them on the comments side, on the comments side of the chat. Okay, so having seen that, now let's move on. So first of all, I want to do a very simple, but before that, let me scale my data. Why do we want to scale this data? So a common question is, should I scale the data? Do I need to scale the data? Why do I want to do that? So the reason you want to scale your data, especially for a numerical data like this, is this. So you want the data set, if you're going to train a model, you want your data on the same scale. Otherwise, for some models pay attention to larger data, magnitude-wise. Some models pay attention to larger data than they do to smaller data, which would not be fair. So look what we have here. Let me go back to the data set so that you can understand what I'm talking about. So look what we have on this data set. So we have median value, median income, which is 8 here. And by the way, this is 8 tens of thousands. This is 8 tens of thousands, so this is 80,000, by the way. And you have house age, which is 41, and then you have average bedroom, which is 1. So we are dealing with a number which is 1, and then we're dealing with another number for median house value. Our median house value here is in hundreds of thousands. So 4.5 here means 450,000 US dollars. So that's the median house value here. So you can see that the values are not on the same range, because we have one which is 1, and then another which is scaled, which is collected in hundreds of thousands. So the scale is not the same, and that's going to impact our model. So if the scales are not the same, you want to scale your data set so that you can have them in the same range. Okay, it helps to make your model fair, so that it's fair to all features. So then this is us scaling our data. First of all, we splitted the data into our train test splits. You already know how to do this by now. And then we call our standard scaler. We already imported our standard scaler up, so we call it here, we instantiate it as scaler, and then we're using the scalar.fit transform. So we're fitting and transforming at the same time. So we use our scalar.fit transform to transform the X train and X test. Okay, we're transforming the X train and X test. We don't need to scale the response variable. There's no need for that. Okay, so we scaled our data sets. So our new X train and test split now is the X train scaled and X test scaled. Those are the new values we're dealing with now. So having done that, the next thing I want to do is to run a simple regression model to give us a baseline model of what we're doing, right? So that we can then compare that against the improved models we'll be having later. So I want to do a quick model so we can see what a simple linear regression would look like. And then by the time we make improvements, we can then compare it against the base model we already had before and then see changes as they happen. So this is us using our baseline model. So we already imported linear regression up above, and then we instantiated linear regression as baseline model, and then we fit X train scaled versus Y train. And then next is we run a quick predict baseline model that predicts. We're using X test scaled to do our predicts. Can you turn off the AC for a moment? Okay, so so that's what we have so far. So if I run this, let me run this. If I run this, this is me splitting the data. And then I also run this. So that's in line. And then if I haven't run that, I already did this before, so we can just move on. So haven't done that, and then I am doing a quick accuracy test on them. So I did the mean square error. I already imported the accuracy scores up above as well. So we have the mean square error, we have the mean absolute error, and then we also have the RMSE score, and then we have the root, the R squared score as well. So we're using this to have an appreciation of how the model performed. So for the first one, just to give you a quick overview as well of what this test scores do. Okay, so this is the result we got after running this. This is the result we got. We got 0.5, 0.555, 0.53, 0.7, 0.57. Okay, so what does this mean? Is this a good result? What can we infer? What can we extract from this result? Okay, so the way to look at this result is, recall that our California housing is in hundreds of thousands. Okay, the housings are in hundreds of thousands. So what this model tells you is, for instance, it's a 0.5. 0.5 would mean that you're off by, if you pick any random house, if you make a prediction for any random house, that you will be off by, say, 50,000. But it's 0.55, so this is 55,000. So you'll be off by 55,000. That's what this is telling you. So our model here will be off by 55,000 US dollars. So is that a good model? Okay. To know if this is good, you might want to see the mean housing. What is the mean housing in California in this entire data set? What is the mean housing? So if you know the mean housing and then you're veering off by 55,000, that might tell you whether you're doing a good job or you're doing a terrible job. Okay, so the mean square error says, okay, if we pick a random house, we'll be off by 55,000 averagely. And then the MAE, the mean absolute error. Okay, just a quick correction though. The mean square error does not entirely tell you that you'll be off by 55,000 because this is a squared value. So it's not calibrated in the exact same units as the property itself. So that's why we really cannot see that because it's a squared value, it's not in the same unit. So what gives us a good sense of the values is the RMSE value, because this is the root MSE. So in this case, we'll be off by 74,000, which is actually a lot. So this is 0.74. So we're off by that, and then the MAE, the mean absolute error, was what I was explaining before. The MAE says you're off by 53,000. Okay, and then the R-square value tells you how much of the variance in your Y value is your model explaining. How much of the variance in your Y value is explained by your X values. Okay, how much of that's what the R-square tells you. How much of the variance in your Y is your model explaining with respect to the X values. So in this case, we have 57. This 57 essentially means 57% of the variance can be explained by the X values. X values here, I'm talking about the response features, the predictor features, which is the various X features we have. So the R-square value says 57% of the variance in Y can be explained by the X features. All right. So that's a quick introduction to accuracy, and then we can then move on. So basically, we are having a 57% score, accuracy score. So 57% is just like an average. It's just like an average score. It doesn't really say, that's not really good, so to say. You wouldn't want to work with 57%. Okay, so just to have a quick drill down to see what our Y feature look like, decided to do a quick box plot. So the box plot says, from what we can see from the box plot, is that we have a number of outliers. We have an extension. Okay, we have an extension and some number of outliers. So our values might not be well concentrated on the median mark. So for the box plot, you have, this is the minimum value here. The mark here says minimum value. So our minimum value is somewhere around less than 10. Okay, for each one of these marks, it actually marks 100,000. So because this is calibrated in 100,000, so each one of these is 100,000. So the one you see here means 100,000, and then the maximum value, the 5 you see here is 500,000 US dollars. So our minimum value is somewhere around here. So though I did a printout of it, so our minimum value is 14,000 US dollars. So the minimum housing in California is 14,000, and then the maximum value is, well, it's around 500,000 US dollars. So the distribution is not very, it's not normal distribution. And so we have quite some. The pricing is skewed towards the upper end. And then so in the middle of this box, the line in the middle of the box represents the median score, and with a few outliers at the very tail end of the box. Okay, so going on further, the next thing we have on this chart is trying to see a visualization of what we have. A visualization of, so just a quick, because what we are trying to do here is we're trying to understand the model, and then as well we're also trying to understand if linear regression will be a good fit. Okay, so the way you still go about it is you also want to check a residual plot. You want to do a residual plot versus the actual features. So plotting your residual versus the actual feature would also give you a good gauge of what you have to tell you if you're really having a good if the choice of a linear model is a good one. So this is what we have here. So calculated the residual from the baseline model, which is y test minus the baseline we already predicted, and then did a scatter plot of it, and this is what we have. Okay, so usually what this is supposed to look like is you're supposed to have these points scattered around, randomly scattered around the 0 mark in no particular pattern. In no particular pattern, it's supposed to randomly scatter around the 0 mark. So the 0 mark is a red line, and but from what we can see is that it's actually not evenly distributed around the 0 mark, because we have some at this tail end, we have some more on the upper end, on the positive end of the line, but on the lower side here we have more values on the negative side. So basically, so from most of what we are seeing, what this is telling is our data set might not very well be represented by a linear model. We'll probe further to see if that is true, but for the most part, our data sets might not be better captured by a linear model. So maybe some other kind of model might do a better job for us, but let's still see. So here is a distribution of our median house, just the median house value, just to still give us a good sense of what we have. So this looks like a normal distribution, but then it has a tail. It has a very long tail. It has a very long tail into the negative end. So it tails down close to minus 10, and then all the way to 4. So this is slightly normal, but not very normal, because we'll have a quite negative tail here, but it's approximately a normal distribution. So the next plot here, which is the residual plot versus the fitted plot, it's also another way of telling you if a linear regression would be a good model for you. So the residual plot here is, in a sense, just like the residual plot versus actual plots that we did here. But here we did a residual versus the fitted values. So we calculated the fitted values. So the plot is this. This is the plot. So residual versus fitted. So we are doing a scatter plot of the baseline model itself versus the residual. So this will tell us how the error, the variances we see in our results is compared against the Y model compares against the predicted values that we have. So these fitted values represent the predicted values that we predicted. So this is a model of the residual versus the predicted values. Okay. So again, this is supposed to be evenly distributed around the 0 mark without no pattern. But what we can see here is that this shows an inverse correlation tailing down. So it's a descending plot, as we can already see from this plot here. It's a descending plot. It's a negative correlated plot. So which is not what we're looking for. It's not what tells you that a model is linear. Again, which gives credibility to the assumptions we're already holding. Okay, the final, perhaps one of the last ways to still draw a very good conclusion in what you're doing is to do a start model. So the start model is an amazing, pretty amazing tool for going about your regression, because the start model provides you with a lot of information in what your data set looks like. Because quite handy information that ordinarily you might not be able to compute. So doing a quick start model can give you it tells you a lot about your collinearity. It tells you more about your whether there are features that are autocorrelated. It tells you about autocorrelation and then collinearity, and then it just gives you a general sense of what's, and then you can even look at it and see how the coefficients of the various features stand out. So we're going to do a quick start model so that we can see the summary result of the start model and have a sense of what our result looks like. So to do the start model, it's very simple. The start model is very simple. So this is our X features, all of our X features, and then our Y feature. Okay, just hold them in different variables, and then call the, we already imported this. Okay, we already imported this add constant up above as well. So the SM, which is the standard. Okay, so the stats model, we imported the stats model above. Okay, we imported the stats model above, and we're going to use it to, before you run a stats model regression, you want to add constants. So the adding constant is just like the constant you have in your regression line. You know, the constant on the Y, the intercept on the Y, that's your constant. So for your regular linear regression, you don't need to add this because the model adds the constant itself automatically as you run the model. But for stats model, you need to add this constant yourself. So that's what we're doing here. We're adding the constant. That's this line. So this is now our new feature with the constant added. And then we're going to use that new feature to fit and run a linear, a stats model using an ordinary linear OLS as ordinary linear regression model. Okay, so this is the process. sm.ols, our Y feature, the one we already computed above, that's this Y here. We're collecting the entire Y feature, and then the constant term that we already have here as well. So which is this, and then you fit that. So if you fit this, you get your model, and then we're interested in the summary result of this model, of this ordinary least square model. So this is what the result looks like. So having done the start model and then the ordinary least square regression results, so what we can see, let's go down and see the tail end of this result. So it says standard error assumes covariance matrix of the error is correctly specified. The condition number is large. It's talking about this number here. It says the condition number is large. This might indicate that there are strong multicollinearity or other numerical problems. So we already have an indication there that there could be a problem with the model, right? So we could have a strong multicollinearity, but remember from our initial introduction, we said that the dual of longitude and latitude showed strong multicollinearity, and then we also have number of rooms and number of bedrooms also strongly multicollinear. Okay, those are things we need to take care of. And then okay, for now, those are another thing to look at is the Dobbin-Watson stats. The Dobbin-Watson stats here shows it's 0.885. The Dobbin-Watson can help you with the IVF. Okay, it can tell you, okay, sorry, let me take that again. The Dobbin-Watson can tell you if your model is autocorrelating. Okay, if it's autocorrelating. correlating, in which case what that essentially means is if there are features that determines other feature, if there are observations that determine other observations. Take for instance, to easily explain this to you, if you're doing a time series model, let's say your time series is running in 2001, 2002, 2003, 2004, okay? So if I pick, for instance, a particular year, 2003, my 2003, the outcome of 2003 is determined or predetermined by 2002. So if I know 2002, I definitely know that my next result will be 2003. So that's an autocorrelation because the current observation is determined by the previous observation. So that's not a good thing because in that case, you don't exactly know whether your model is performing well because features are autocorrelating. So that's what the Dubbin-Watson tells you, whether your model is autocorrelating. So the way you read the Dubbin-Watson here is if the value is approximately 2 means it's not autocorrelating. But if it's less than 2, if it's less than 2 or greater than 2, that definitely means an autocorrelation. So in this case, our result here is approximately 1. So it's less than 2. So that means we have a problem of autocorrelation with this data set as well. All right. So, and lastly, I did a VIF, variance inflation factor plot here. The variance inflation factor plot is also another good way of putting a nail on multicollinearity. Okay. So you want to see if features that are multicollinear so you can remove them. So doing this, looking at the results, forget about the constant feature. So the way you read this is values that run from 0 to 2. 0 to 2 is 2 to 5 is you can work with, right? You can work with values around from 2 to 5, but anything above that you cannot work with. There's a comment section I need to respond to. Okay. So somebody says we can't see the long tail. Scroll down, please. We can't see the bottom of your screen. Okay. Someone said they cannot see the bottom of my screen. Can you see it? Let me verify that. Someone cannot see my screen very well. I need to be sure. Can you see my screen? Okay. How about now? Okay. Okay. Someone said they cannot see the screen. I suppose maybe that's as a result of the way that this YouTube live stream works. I mean, there's a lag in what I'm displaying and the time it takes you to see them. But I just hope that there is no lag in the display with respect to my voice. Okay. But other than that, I hope it's good. I hope it's good. Okay. So again, let's get back to it. So looking at my data sets, I'll do a quick check here. I sort of escaped my mind the IVF range, the range for correction in IVF. So I'm going to ask ChatGPT, how do I read IVF? So how do I read IVF? So, okay, that's a different IVF. So how do I read IVF, meaning variance, okay, not IVF, but VIF, variance inflation factor. Okay. Okay, so 1 VIF of 1 means no correlation between this independent variable and the other variable. Less than 5, 1 to 5, moderate correlation, and greater than 5 means high correlation. Correlation which might be of significant problem. And then 5 to 10 means consider removing it. Okay, so if we come back to it, so for med income, housing age, no problems. So the problem starts with house, average room, and average bedroom. So that confirms what we already know. The correlation here is above 5. That's 8 and 6. That's a problem. And then latitude and longitude, we have a correlation of VIF of 9 and 10. So 9 and 8, which is also a major problem. So we have to deal with those. And then the way to deal with this is we can either do a log function, or we can use some other non-linear models, or we can apply some other means of adjusting our data, like maybe a square root, instead of a log function, maybe a square root function on the data set to sort of try to straighten them out. Or sometimes you can do a feature selection, like you're dropping an entire feature just so you, for instance, between longitude and latitude, we might want to drop one of the feature, the one with the less impacts, like we might want to drop longitude, okay? So there are a number of ways you deal with problems like this. There is no one solution fit all for handling these problems. So, and a good thing to keep in mind is that if you're doing this, you can ask the AI ChatGPT, how can I handle multicollinearity? How can I handle the features? Then it will give you a plethora of options. And then you, as a data scientist, a major part of our job is to iterate. Is to try out a number of things and see which one returns better results. So data science, it's not all scientific as it's more of a try and error process. You try, you go back, you adjust, you try again. You just keep switching between parameters and hyperparameters, and then until you find something that is ideal for your particular case. Okay. So having shown that, okay, one way I want to consider dealing with this is, instead of doing an ordinary least square regression, I might want to consider a lasso or a ridge regression. So the lasso, for instance, has a way of handling multicollinearity and some of these problems. And what does the lasso do? The lasso essentially penalizes features that do not contribute very well to the model. It penalizes them by grinding them to 0. So it renders the coefficient 0 so that other features can have more prominence in the model training. Okay, that's what the lasso does. But the ridge, on the other hand, does not grind features to 0. Instead, it sort of gives values. It's an arbitrary value it computes, and then it gives, instead of running down features to 0, it gives more credits. It gives more worthiness to features that contribute more as opposed to features that contribute less. Okay, in that case, you're able to give more prominence to features that are more important to the model. So that's for ridge and lasso. So we'll train a ridge and lasso model and see if they perform better than the baseline that we already have. Okay. So with training our ridge model, so I import a ridge, a lasso up above. I already imported lasso up above. So I'm instantiating the lasso, and then I'm setting my random state to 42, and then I'm using alpha. Alpha here essentially says the weight of the penalty, you know, by what degree you want to penalize the coefficients. That's what the alpha here represents. So I'm going to be doing, these are, by the way, these are generic numbers that they try out your model on. So I'm going to go from 0.01 to 0.0, then 0.1. Then I'll see at the end of the day which number, which alpha returns better results. And I'm going to be doing this on a grid search. Okay, on a grid search, so that I am able to iterate instead of just using my single train test data set. I want to set a CV of 5. Okay, I want to set a CV of 5, so that what this will do for me is that for every number of time I'm training this model, because I'll be testing these different hyperparameters, so I would first of all test them on different subsets of the data set. So I'll be dividing my data set into 5 different parts, and then I'll train on 4 sections or on 4 parts of it, and then I'll test on a single part of it. So that's why I split into I'm doing a CV of 5. So I'll be training on 5 parts of the training data set, and I'll be testing with 1 part. So I'll be switching sites. And so this actually would take a lot of computation power, because what we're doing here is we're testing each one of this, and then it's not just that, because for each one we test, we'll be testing on different parts of the data set. So it's sort of like a grid, a 5 by 5, a grid that's 1 by 5 grid, in which case you use 4 parts to train and 1 part to test, and then you switch it again. You use the other one to test, and then another set of 4 to train. So you keep doing that until you use out the entire part of the data sets, and then you compute the average. So you try out this different number of sections of your data sets, and then you compute the average. The one that returns, you compute the average and use that as your outcome. So what this does is that it helps when your data set is not much, and then it also helps to making sure that you've tried out the average number of data sets. It helps with reducing overfitting as well. So this is a good way of testing, of training a model. So that's what we'll be doing here. So having done that and fitted the model, and then I am computing lasso grid.best estimator. So because I've done a number of trials around my alpha, I would want to see the best estimator. So luckily, start model already have an estimator that can return the best performing one for you. So I've computed the best estimator and saved it as best lasso. And then on here, I did a predict using the best estimator. I want to do a predict for my test data set, and then I've saved that as Y predict for lasso. Okay, and just exactly what I've done here. It's the same thing I'm doing for ridge regression. And then I've also saved the best ridge regression, having tested out all the alphas. And then I've also done a predict using the best ridge regression. Then I've saved that. And next, what we need to do is to see the outcome of, to see the outcome, the accuracy of the model. So on the side of accuracy, I have here, so the way I want to go about doing this, instead of doing them one by one, just wrote a simple for loop to help me compute it at once. Okay. So what this loop will do is, so I say for name, comma, y predict in lasso, y predict lasso. That's this y predict lasso and y predict reach, y predict reach. So this is a tuple that I'm holding in a list. So for my first y, because I'm doing a for loop, for my first iteration, I'll be holding this first element of the tuple. So my name now will be lasso, and my y predict will be the lasso prediction I already computed. Okay, so that's for my first iteration. So essentially what I want to do is I want to now say, okay, compute using this y predict, compute my y test, and y predict. So I'm doing mean squared. Y test is half. We already have our y test value. Okay, and then I also want to do my y predict. Y predict is this one here. So recall that this one here is holding, for my first iteration, it will be holding lasso. So I want to use my lasso to compute my mean square. Also use lasso to compute absolute value. I just want to do it for the rest of the accuracy scores. Okay, and then I want to print out the results. So the name I'm holding here is this name, lasso, because I said for name, comma, y predict. So the name here is this lasso. So just so you know which result belongs to what model, that's why this is necessary. So I want to print out the name, which is lasso, and then the regression. So these are the different regression results. So this is what that looks like. Okay, so I'm seeing all the outcome on here. And then I did exact same thing, which is the next iteration. So if I've gone the first iteration, the next iteration comes in, and that would be my reach. Okay, reach, and then it's holding the reach regression, and then it will run along and then give me a compute value. And then I have all this. And then looking at these results, this is the best alpha. This is the best alpha for lasso, and this is the best alpha for reach. And then this is the outcome. So this outcome is not too different from what we had before. Okay. Recall that when we first used a simple linear regression, we had a test score of 0.55, 0.53, 0.74, and 0.57. And now that we've used lasso and reach, our result didn't change that much. Our result didn't change that much at all. It's essentially nearly the same kind of results. Okay, so which means the persistent problem, the problem we have is still we still haven't fixed it. And so, but because the lasso would have solved the problem of multicollinearity for us, and yet we still didn't have much change in our results. So the next best thing to do will be to try out a non-linear model. Okay, a non-linear model might be the best option to fit in our data, because then maybe the data is not entirely linear. Maybe there's a bit of a spline sheet. A spline sheet model might do a good job for us, or maybe a random forest could give us the kind of results that we need. Okay, so again, this is how you build your model out. You try out your options, you test them, and then you go back, you try again, you test them, you go back, you try again, you test them, until sometimes you can be working through your model and then it could take weeks before you arrive at the kind of results that you want. But once you have that result, you can then optimize that result and then get going from there. Okay, so this is to help me visualize the outcome of the results, to see it, to help us make sense of it graphically. So I'll walk you through the code, but first of all, let me explain the outcome. So this is just a scatter plot of the values that we have, of our test values, a scatter plot of them. Okay, so having done this scatter plot, the orange line represents what an ideal model would have looked like. Okay, with this orange line, or the broken black lines, showed what an ideal model would have looked like. Okay, but now the ridge and lasso regression is this one here. They both fall in overlap, so the both of them are on here. So that's the green line here. So you can see the divergence, quite a clear divergence between our lasso and ridge from what's an ideal, what an optimized model may have looked like. Okay, so because of this divergence, we're not able to get good results. This is quite a steep divergence. So that's why the model is not giving us the results we want. So back to this code. What this code, let me just run you quickly through the code. So this is for the fig. I'm using a plot canva of 12 by 8. That's this entire size, 12 by 8. I can expand it if I so wish. And then I want to do a scatter plot. I want to do a scatter plot of the different models. So first of all, I PLT.scatter. I did a scatter plot of just plotting the actual value against itself to just give me the straight perfect regression line. Okay, that's this represent here the the orange line. Okay, this orange line is giving me my actual value as a straight line, so that the other models should come close to it. Okay, and having seen that, I also have a perfect line as well. So the perfect line is just what an ideal value should also look like. And then there's an overlap. The orange line is there and the perfect line is right on top of the orange line. Okay. So explaining this quickly. So I'm plotting y-test against y-test. So on top of each other, so that I can have a straight line from which I can judge the rest of my model. So I'm using an alpha of 0.5. That's how thick the coloration of the line should look like. And then I'm naming it. So I'm also doing a scatter plot of the test value versus the predicted baseline. So what I'm trying to do here, I'm trying to see how each one of the points deviates from the exact points that we already have. How each one of the points deviates from the original plot. And then I also did that the same thing for the model. So the baseline plot is the red colored one. And then we have, for the lasso, we have the blue, and then the green for the ridge. So the green is for the ridge, and because it's the last one, that's what you're seeing. The rest of the data are it's overlapping points. So if you look very well, you see that the blue one for the ridge is underneath the green, and then similar thing for the red orange, for the red baseline model. Okay. I think I hashed out the baseline model. I did not run it. Okay, but that's for the scatter plot, and this here is for plotting the broken line, plotting the perfect fit. So what I did here was to generate the best results, the minimum value for my Y test, Y predict baseline, the lasso, and then the ridge, and then the maximum value for all of them as well, and then just do a plot that runs from the smallest value to the maximum value, and that's this plot, which also coincided with the ideal plot as well. There I can see how my other plots deviate from them. So here is a range. This np.line space minimum value, maximum value generates 100 points. Reshape them. What I want to do is I want to make a plot. I want to generate values across the x-axis that I would use to plot my lines for each one of these models. So I have my plt.plot, which is for the different models. I want to do a plt.plot x range, lasso, and lasso.predict x range, color of blue, and then I'm labeling this lasso regression. That's the color of blue, the blue colored one. So X range is this range that we have here. This range is 100 values. Okay, 100 values splitted equally from the minimum value that we have to the maximum value that we have. That's what this X range is here. So I have 100 different values plotted against my lasso as well. And then for my lasso, I'm also Borest well. So I'm giving it the X range so that it can do the prediction and then plot the values for me. Okay, recall that the X range runs from the minimum to the maximum value, splitted into 100 places. And so that's what I have here. This exact same thing I did for the ridge as well. This is it for the ridge. So the reason we want to do this is so that we can see by what degree our model is veering off from the exact thing, from what should be an ideal model. So these are just labeling the plots and then showing the plots. Okay, so that's what we have here. Okay, next we want to. Okay, so from what we've gathered so far, we can see that a simple linear regression is not particularly generalizing as we would have wanted. So this next code was to try out a random forest. Okay, so imported a random forest, scikit-learn, using still our grid search so that we can have different test outs. Okay, if you're going to try this will take quite a number of time to render, and then it will still be better to do this on Google Colab so you don't use up too much space on your laptop in doing this. So we're using a number of number of trees that we have ranging from 100 to 200 to 300, and then maximum depth. So these are all hyperparameters we want to test out. Okay, and this is us actually building the model. So, and then the results of the model we want to see at the end of the day. This is our best aggregator, and then we want to see the results. So let's try out, let's see what these results will look like at the end of the day. I will go on here and copy this. Okay, so I want to see the results for using a random forest, how that would compare with all of the other things that we've done. Okay, so this is us predicting this is the outcome of our predicted value, and that's our y predicts here. So I'll switch that. So before I run this, let me see. Okay, voila. So looking at this, we can see a significant improvement from 0.5 to 0.2. That's a lot of improvement. So I would want to test this out on all the other accuracy scores. Okay. Okay, so let's print this out and see what we have here. So I'm going to do print. Okay. So I'm going to use string formatting. So for the first one, we have MSc, and the results we got there was okay. The result we got there was, how do you use this? Let me just type it out. It's showing me it's prompting me, but if I try to select it, it's giving me something else. Okay, so this is for MSE, and I'll just courage enter to do for the next one, which is MAE. This is exactly what I want. Say way to tab, right? Okay, perfect. Okay, so if I run this whole thing, whoa, okay. Okay. I've not changed the values for the rest of them. Copy this. Replace it with this. Okay, so we have y-test, and r square, y predicts rf. Okay. So let's run this again. Okay. So this shows quite some improvements. So our MSE went from 0.5 to 0.25, 0.55 to 0.25, and then the MAE went from 53 to 32. Okay. So instead of dealing with 53,000, we're now dealing with 32,000 for MAE value. So we can already see that so far we've got some improvement in the model. Okay, but this model can even be made even more better if we decide to do a truly non-linear model on this. So because essentially as data scientists, that's what the job is. You want to try out any number of, and then looking at our R square, we've moved from 50% to 80%. Okay, that's a significant jump so far, right? So we can see that we really can actually improve the model if we work on it, especially there are a number of things we can still do to this model to really get it to where we want it. Stuff like doing some of the feature selections ourselves, and especially using a non-linear, particularly I think this model would do way better if we try out more number of non-linear models. Okay, that could help us, that could help the model generalize better and follow the pattern better. But in any sense, we've been able to get the model from 0.5 to 0.25, and then from 50% accuracy to 80% accuracy results. And so, by and large, that is it with this course. And then, simply put, for the purpose of why we are having this lesson, okay, but before I get down to that, to the end of what I want to say now, I would want to see the comment section and respond to some of the things people are saying on the comments. Okay, so someone said, and this is from Prince. Prince said, why did you use squared equal force in the RMSE? Kindly explain the impact when used and when not used. Okay, thank you very much, Prince. And so the squared equal force for your RMSE is just so the mean squared error function here. This is an inbuilt flag. An inbuilt flag to say, okay, I don't want you to give me, I want you to give me the squared, I don't want you to give me the squared value. The squared value would be the MSE, mean squared error. So, but when you said this mean squared error, recall that the mean squared error function is the same thing we're using here, mean squared error, mean squared error. But the two of them are giving us different results. So if we didn't put the squared equal force, this would have essentially given us the mean squared error back, right? So because this function, mean squared error, is supposed to give us the mean squared error. So, but when we flag it to false, it means we don't want the squared. We want the square root. Okay, instead of squaring it, it will give us the square root. Okay, that's the RMSE value, which is the root mean squared value. That's the square of the MSE. Okay, I hope that explains, that answers your question. If you're still not very clear, please quickly drop a comment. Do we have any more comments? Okay, guys. Okay, so if anybody has anything to say, any question to ask, please feel free to. Is there a question on WhatsApp? There's a question on WhatsApp. Okay. Furthermore, you can leave your questions on WhatsApp as well. We'll respond to them. It's an ongoing process. If there's anything confusing to anybody at any point, We're on this journey together. At the end of this journey, the goal is in way of portfolios, getting your hands dirty and trying out things. You're also building up, you're also strengthening your skills, your ability to do this, to work as a data scientist. You're strengthening your skills. So that is it. That is it. Thank you for very big thanks to everyone that joined this session. Please, something else we would want to do is to sort of give this some presence on Twitter. That was why Austin initially said the link will be dropped on Twitter so that you can give it a like and a follow. We should follow each other on Twitter so that we can as well build up some social presence outside of WhatsApp. Okay, so please do well by trying to follow the Twitter handle and give it a like. Thank you very much for joining the session. So tomorrow, please, we'll be working on GitHub, okay? Because a very good GitHub skills is not something it's not an optional skills to have. It's not something you want to or don't want to. It's a must-have, right? You want to be able to push codes to GitHub, right? Whatever you're working on, you want to be able to push them. So tomorrow we'll see how to push these codes on GitHub, create your GitHub profile, simply push your codes to GitHub so that, and then collaborate with other, if you want to work with people as well, so that you can collaborate on projects on GitHub. So that's what we'll be looking at tomorrow. After which, we would also build up a simple UI interface of this entire project. And then, of course, the cloud part of it. How to go from running your model, pushing them on GitHub, deploying them on cloud, and then building a UI presence for them, and then deploying them on cloud. So it's the complete package. It's the complete package, and every process of this is going to be extremely enlightening. So thank you for joining again. Bye for now.